In the last two lectures, we focused on Euclidean domains, covering the material of section 8.1 of Dummit and Foote. And in this lecture, we'll focus on PIDs, principal ideal domains. We'll mostly cover material from section 8.2, but we'll also cover some of the things from early on in section 8.3. So before jumping into that material, I would like to review some things that we proved last quarter. In particular, some material from section 7.4 of Dummit and Foote on properties of ideals. So first, what does it mean for an ideal to be a maximal ideal? Let's let S be an arbitrary ring. An ideal, M in S, is a maximal ideal if it's not the whole ring, and the only ideals containing it are M itself, the ideal itself, and the whole ring. We proved that in the case where R is a ring with identity 1 not equal to 0, and you have an ideal I and R, we saw when I is equal to the whole ring, that I is equal to R if and only if I contains a unit. Then, looking at the case where R is also commutative, we saw that ideals in fields have a particularly simple structure, that R is a field if and only if its only ideals are 0 and the whole ring R. So the ideal structure of fields is particularly simple to describe. We proved then that if R is a commutative ring with identity 1 not equal to 0, and M is an ideal of R, there's an easy way to tell if M is a maximal ideal. That M is maximal if and only if R mod M is a field. And the idea is to look at the lattice isomorphism theorem that relates ideals in R containing M to ideals in the quotient R mod M, and then to use this result from before. Okay, so we know what it means to be a maximal ideal in an arbitrary ring. We also studied prime ideals, but in order to define a prime ideal, we want to suppose we're in the case that R is a commutative ring with identity 1 not equal to 0. An ideal P of R is prime if it's not equal to the whole ring, and whenever A times B is in the ideal, that means A is in the ideal or B is in the ideal. So whenever a product of two things in R lands in the ideal, one or the other of those elements had to be in the ideal already. Okay, so we proved the analog of this result where you can see whether an ideal is maximal by taking a quotient for prime ideals. So let's say R is a commutative ring with identity 1 not equal to 0, and P is an ideal of R. Then P is prime if and only if R mod P is an integral domain. And the way that we proved this was just to translate the condition of what it means to be prime over into this quotient ring and see what that means. All right, so now we know that every field is an integral domain. It's not true that every integral domain is a field, but it's certainly true that every field is an integral domain. So that means in this setting where R is a commutative ring with identity 1 not equal to 0, every maximal ideal of R is a prime ideal. Okay, so I'll pause and erase, and then we'll see what happens if you suppose that you're in a ring that has extra structure, like for example, what happens when R has the additional property of being a principal ideal domain. We'll now prove that every non-zero prime ideal P in a PID is a maximal ideal. So we know that maximal ideals are always prime, but in a PID, prime ideals are always maximal. So in a PID, the concept of being a prime ideal and being a maximal ideal are the same. Let's prove this. So we want to take our prime ideal P and show that it's a maximal ideal. Well, since R is a PID, this prime ideal is principal. So that means that it's generated by P for some element little p in R. All right, so how are we going to show that this is a maximal ideal? Let's suppose that it's contained in an ideal I of the ring R. The idea is going to be that we'll show that either I is equal to P or I is equal to all of R. So before I say that, R is a PID. So what do we know about this ideal I? It's principal. So it's generated by M for some element M in R. And now we need to show that this ideal generated by M is either the same as the ideal generated by P, or the ideal generated by M is the whole ring R. All right, so what do we know? So we know that the ideal generated by P, that is P, is contained in I, which is the ideal generated by M. So that means the element little p is in the ideal generated by M. So that means, what does it mean to be contained in a principal ideal in a commutative ring with identity? That means that P is equal to R times M for some element little r in the ring. So, okay, P is equal to R times M. That means that R times M is contained in the ideal generated by P. And why would we think to look at that? Well, that tells us something because the ideal generated by P is a prime ideal. So once we know that Rm is in this prime ideal, either R is in that prime ideal or M is in that prime ideal. Let's just consider each of these cases separately. If M is in the ideal generated by P, then the whole ideal generated by M is a subset of the ideal generated by P. But now we've shown inclusion both ways. So these two ideals are the same. So now let's consider the case where R is in the ideal generated by P. So what does that mean? R is in this principal ideal. So R is equal to P times S for some S in the ring. But okay, so what do we know? We know that P is equal to Rm and R is equal to PS. So P is Rm and R is PS. So P is equal to P times S times M. And okay, you subtract from both sides, you factor out a P, you see that P times Sm minus 1 equals 0. And since R is an integral domain, that means that Sm has to be equal to 1. So what does that mean? We're in this commutative ring, Sm is 1, Ms is 1. That means that S is the inverse of M. So M is a unit in the ring. So what's true about the ideal generated by M is it is the whole ring. So what have we seen? We've seen that the only ideals containing this prime ideal P are the ideal generated by P and, or sorry, the ideal P itself, and then the whole ring R. So this is a maximal ideal. Okay, so let's stop and think for a second about examples of how ideals in a ring relate to ideals in the polynomial ring in one variable over that ring R. So the first example that you might think of is we know Z is a PID, but Z bracket X is not a PID, right? Because why not? Well, we showed that the ideal generated by 2 and X, that's an ideal in Z bracket X that is not principal. So it's not true that if you have a ring R that is a PID, that R bracket X is a PID. So that's something that sounds like plausible, but it's just not true. On the other hand, we do know that if F is a field, which is stronger than being a PID, if F is a field, then F bracket X is a PID. Why is that? Well, we showed even more. We saw that F bracket X is a Euclidean domain, which means that it is a PID. So these two examples, if you keep them in mind, sort of will help you to remember what the general result says, which is, okay, so suppose you have a ring R that's commutative, and you know that R bracket X is a PID. So what has to be true about R? R must be a field. So Z, not a field, Z bracket X, not a PID. So, and F field, F bracket X is a PID. So this is the way to remember what's going on here. If you start with R bracket X being a PID, the only way that that possibly could have happened is if you started with a field R. Okay, so I'll pause and erase, and then we'll prove this result. Let's prove this result, that if R is a commutative ring such that R bracket X is a PID, then R must be a field. So let's suppose that R bracket X is a PID. Well, note, R bracket X has an identity if and only if R does. So that's something that came up when we first were discussing polynomial rings in section 7.2. And what else? R bracket X contains a subring isomorphic to R given as the polynomials of degree 0. So R bracket x is a PID. That means R must be an integral domain. There's no way for R to have any zero divisors, because then R bracket x would contain these zero divisors as well. And a PID is an integral domain, so you can't have any zero divisors. So OK, R has to be an integral domain. Now we're in a position to use some of the results that we have from earlier. The ideal generated by x. What is true about this ideal? Well, R bracket x mod the ideal generated by x is isomorphic to R. If you mod out by this ideal generated by x, you're just getting representatives are the polynomials of degree 0. So R bracket x mod the ideal generated by x is R, which is an integral domain, which means that the ideal generated by x is a prime ideal. And now, the ideal generated by x is a prime ideal, but it's a prime ideal in a PID. And in a PID, every prime ideal is a maximal ideal. So the ideal generated by x is maximal. So that means not only is R bracket x mod the ideal generated by x an integral domain, but it's actually a field. And because it's isomorphic to R, R must be a field.